every single thing you see around you right now, like the specific shade of paint on your walls or the blue of the sky outside, even the device you're listening to this on, all of it is the result of an incredibly complex biological camera.
Right.
And, it's working in perfect silent harmony with the physical properties of light.
Yeah, we move through our days completely immersed in this visual data. And yet, it's so seamless, we almost never stop to consider the sheer amount of, well, physics and biology required just to process a single glance.
Totally.
I mean, our eyes are open, so we just assume we're seeing reality exactly as it is.
And that assumption is exactly what we're going to challenge today. Welcome to this deep dive. We are exploring a really fascinating stack of source material today, all about the human eye and the incredibly colorful world around us.
It's a trade topic.
The goal here is to basically unpack the mechanics of how your eyes capture the world, like what's actually happening when that biological machinery goes wrong, and the invisible physics behind why the sky looks the way it does.
Exactly. And by the time we finish this discussion, you're going to look at a simple sunset, or a starry night, or, even just the eyeglasses sitting on your nose, with a completely renewed scientific understanding.
I know I did after reading this.
Yeah, you realize that much of what you think you're seeing is actually a highly orchestrated illusion.
So if we want to understand the colorful world outside, we really have to start with the hardware inside our heads that lets us perceive it, right? We need to talk about this biological camera.
You do.
To set the stage, the human eyeball is roughly spherical, and it's only about 2.3 centimeters in diameter.
Which is tiny.
It is. It's remarkably tiny when you consider the sheer volume of, high-definition video it processes every single second.
It's an incredibly compact piece of engineering.
Yeah.
I mean, if we trace the journey of a single beam of light as it enters that 2.3 centimeter sphere, the very first thing it hits is the cornea.
Right. That's the transparent kind of bulging surface right on the front of your eye.
Exactly. And what most people don't realize is that the vast majority of the actual bending or the refraction of light happens right there.
Oh, really?
Yeah, at the outer surface of the cornea before the light even gets deep into the eye.
Wow. Okay. So after the cornea does that initial heavy lifting, the light passes through the iris, which is the dark muscular diaphragm that gives your eye its specific color, right?
That's the one.
And the iris controls the pupil, widening or shrinking that opening to regulate exactly how much light is allowed in.
Right, like an aperture on a camera.
Exactly. But once the light gets past the pupil, it hits the crystalline lens. And this seems to be where the real optical magic happens, because this lens is responsible for the fine focal adjustments. It takes that light and projects an image onto the retina at the very back of the eye.
And we really have to pause here and look at how that image actually lands on the retina. Because the crystalline lens in your eye is a convex lens, meaning it bulges outward in the middle.
Oh.
And the physics of refraction dictate that the image it projects onto the back of your eye is a real inverted image. It is entirely upside down.
Okay, let's unpack this, because that is wild to me. The biological lens inside my head is projecting an upside-down movie of the world onto the back of my eyeball.
Yes.
But when I look around the room, I certainly don't see the world upside down.
Well, that highlights just how much of your vision is actually synthesized in your brain rather than just captured by your eye.
Right.
The retina is packed with millions of light-sensitive cells that convert that upside-down optical image into electrical signals. Those signals shoot down the optic nerve, and your brain flawlessly, instantly flips that data right side up.
It's basically a seamless software correction happening in real time.
Every waking second of your life, you never feel it happening.
And the physical hardware adjusting that image is just as impressive, because you can look at a mountain range miles away and then instantly look down at a text message right in front of your face, and, both are perfectly in focus.
Right, the source material calls this the power of accommodation.
From what I understand, it operates a lot like the autofocus on a smartphone camera, but the mechanics are entirely different, aren't they?
Very different, yeah.
Because instead of sliding little glass lenses back and forth inside a metal tube, your biological autofocus relies on these things called ciliary muscles to physically squish and stretch a fibrous, jelly-like lens.
That is precisely how it works. It is a highly physical process. When you look at that distant mountain, your ciliary muscles relax.
Okay.
This allows the crystalline lens to stretch out and become thin, which increases its focal length and brings the distant object into sharp focus on your retina.
But the moment you look down at your phone...
Those same ciliary muscles have to contract. They actively squeeze that jelly-like lens, making it thicker and more curved. That decreases the focal length so you can process the image up close.
It's actual physical labor.
It really is.
I mean, it makes total sense why your eyes physically ache after staring at a computer monitor for 9 hours. You are flexing a muscle continuously.
Yeah, and there are physical limits to how much that lens can be squished. The closest distance you can hold an object and still see it distinctly without straining your eyes is called the near point.
And for a normal young adult, that near point is about 25 centimeters away, right?
Exactly. If you bring something closer than that, those ciliary muscles simply cannot squeeze the lens any thicker and the image just blurs.
Got it. On the flip side, the far point for a normal, healthy eye is literally infinity. You can focus on stars that are light years away.
You can,
Yeah.
but, biology is rarely perfect forever, which brings us to the inevitable failures of this system.
Right.
What happens when that brilliant biological autofocus starts to lose its flexibility, or what happens when the physical shape of that 2.3 centimeter sphere isn't perfectly round?
Well, we all know people who are nearsighted, like they can read a book perfectly fine, but they have to squint to read a street sign down the road. This is called myopia.
Right.
But mechanically, what is actually failing inside the eye to cause that specific blur?
Structurally, myopia means the light rays coming from that distant street sign are converging too early. Instead of the image coming into sharp focus directly on the retina, it comes into focus in front of the retina.
Okay, so it falls short.
Exactly. By the time the light actually hits the back of the eye, the rays have started to spread out again, creating a blur. This usually happens for one of two reasons.
Which are?
Either the curvature of the eye lens is too extreme, or the eyeball itself has become physically elongated from front to back.
Oh, so the biological hardware is just slightly the wrong shape.
Exactly. And the fix is a simple application of physics. We place a concave lens in front of the eye.
A concave lens being thinner in the middle.
Right, and it slightly diverges or spreads out the light rays before they even reach the cornea. By spreading the light out first, it delays the convergence, pushing that focal point back perfectly onto the retina.
That makes perfect sense. And the exact inverse of that is hypermetropia, or farsightedness. This is where you can clearly see the street sign, but the book in your hands is a blurry mess. In this case, the focal point of the near object is landing behind the retina, right?
Yep, the eyeball is slightly too small, or the baseline focal length of the lens is simply too long.
To correct it, you use a convex lens, thicker in the middle, to start converging the light rays a little earlier, pulling that image forward onto the back of the eye.
Exactly right.
But wait, there is a third refractive defect mentioned in the text called presbyopia, which also makes it incredibly hard to see things close up. People end up needing reading glasses for it.
They do, yeah.
So if hypermetropia and presbyopia both make it hard to read a menu at a restaurant, are they actually the same glitch in the system?
See, this raises an important question, because while the daily symptom is identical, the mechanical failure is entirely different.
Oh, really?
Yeah. As we just discussed, hypermetropia is a structural geometric issue. Your eyeball is physically the wrong shape. Presbyopia, on the other hand, is strictly a matter of aging.
Oh, I see.
Remember those ciliary muscles that have to squeeze the lens for close-up vision? As we get older, those muscles gradually weaken. Furthermore, the jelly-like crystalline lens itself loses its youthful flexibility.
So the hardware just gets tired and stiff.
Precisely. It simply cannot contract enough to make the lens thick for near vision.
Wow.
That's why someone might suffer from both myopia and presbyopia at the exact same time.
Wait, both at once?
Yeah, their eyeball is too long, making distant things blurry, but their aging muscles can't squeeze the lens, making close things blurry too.
Oh, man. That is when you see people wearing bifocals.
Exactly. The top half is a concave lens to fix the distance geometry, and the bottom half is a convex lens to help the tired muscles read.
There is also a completely different kind of aging defect, though. Cataracts. This isn't about the shape of the eye or the strength of the muscle.
No, it's not.
With cataracts, from what I read, the crystalline lens itself physically breaks down and becomes milky and cloudy, basically blocking the light from getting through.
Right. And that requires surgery, where they actually remove that cloudy biological lens and drop a clear artificial one in its place.
It's a remarkable procedure. But while glasses and routine surgeries can fix these mechanical and age-related errors, there are other defects that require a much more profound human intervention.
Yes, there are.
And this brings us to a surprisingly moving reality regarding corneal blindness. This part of the deep dive really struck me, to be honest.
It's very powerful.
When the cornea, that clear front bulge of the eye where all the refraction happens, becomes permanently damaged or opaque, No amount of glasses or laser surgery can fix it. And the numbers are incredibly stark.
They really are.
There are roughly 35 million people in the developing world who are blind, and of those, about 4.5 million have curable corneal blindness.
Right. And the most tragic element of those statistics is that 60% of those 4.5 million people are children under the age of 12.
That is just heartbreaking.
It is. Their blindness is entirely curable. The medical technology exists, but the cure requires a physical corneal transplant, which means they rely entirely on eye donation after someone passes away.
The logistics of that donation process are fascinating, and honestly a lot less daunting than I imagine.
How so?
Well, the eyes have to be removed within 4 to 6 hours after death. The procedure itself only takes 10 to 15 minutes, and it leaves absolutely no physical disfigurement to the donor.
That's a huge point to make.
Yeah. But I think the biggest hurdle is just the sheer amount of medical misconceptions out there about who is actually allowed to donate.
Oh, absolutely. There's a pervasive myth that you need perfectly healthy 20/20 vision to be a donor.
Right.
But the reality is that people who wear thick glasses, people who have had cataract surgery, and even people with chronic conditions like diabetes, hypertension, or asthma,
Right.
they have perfectly healthy, usable corneas.
That's so good to know.
The restrictions are primarily limited to highly communicable diseases. If someone passes away with AIDS, hepatitis B or C, rabies, cholera, or tetanus, they cannot donate.
Hmm.
But the vast majority of the population can.
Here's where it gets really interesting for me. I always assumed organ donation was like a 1-to-1 ratio.
One donor, one recipient.
Exactly. One donor means one recipient gets their sight back. But according to the medical data, one pair of donated eyes can give vision to up to 4 corneal blind people.
It's an incredible triumph of medical efficiency. Surgeons can utilize different layers and sections of the donor tissue for different patients depending on their specific needs.
Wow.
If we connect this to the bigger picture, it highlights why understanding this biology is so vital. When you realize that your flawed, nearsighted, astigmatism-riddled eyes could still fundamentally change the lives of up to 4 children after you're gone.
It drastically changes the calculus of checking that donor box on your driver's license.
It really does.
It's a powerful reminder of how much we rely on this biological machinery. But if that is the biological hardware we used to see, what exactly is the data it's processing?
Because an autofocusing lens is useless without light.
Exactly. But light itself is playing complex physical tricks on us before it even hits our cornea. Let's unpack the rainbow.
To move from the biology of the eye to the physics of light, we have to look at the classic triangular glass prism.
Okay.
When a beam of pure white light enters an angled glass prism, it gets refracted, or bent. But it doesn't just bend the beam of light as a single unit. It triggers a phenomenon known as dispersion.
And dispersion is the splitting of that white light into its separate constituent colors, right?
Yes.
You get the classic spectrum: violet, indigo, blue, green, yellow, orange, and red. So if you think about it, white light is essentially a zipped folder on your computer.
Oh, I like that.
Right. It looks like one single unified file as it travels through the air, but when it hits the dense glass of a prism, it unzips into 7 distinct color files.
That is a perfect way to visualize it.
Hmm.
And the reason it unzips is because each color of light has a slightly different wavelength.
Okay.
Because of those different wavelengths, they interact with the glass differently, and therefore they bend at slightly different angles. Red light has the longest wavelength, so it bends the least. Violet light has the shortest wavelength, so it bends the most.
Just this differential bending spreads the colors out into a fan.
Exactly.
Isaac Newton was actually the first person to prove this using a glass prism. But the genius of Newton wasn't just splitting the light. It was what he did next.
He always had to take it a step further.
Always. He looked at that splayed-out rainbow of colors and wondered if he could unpack them even further. So he put a second glass prism in front of the spectrum to see if he could split the blue light into entirely new colors.
But nothing happened.
Right.
The colors wouldn't split any further. So Newton tried a brilliant alternative.
Mm-hmm.
He took that second prism and he inverted it. He turned it upside down. By passing the splayed-out rainbow through an upside-down prism, the opposite geometry forced all those different wavelengths to bend back together.
Wow.
Yeah, they recombined, exiting the second prism as a single beam of pure white light. He essentially reverse-engineered the rainbow, definitively proving that white sunlight inherently contains all the colors of the spectrum.
Which perfectly explains how natural rainbows work out in the wild. Obviously, we don't have giant glass triangles floating in the atmosphere.
No, we don't.
But immediately after a rain shower, the sky is filled with millions of tiny suspended water droplets. And every single one of those droplets acts as a microscopic prism.
Yes, but the geometry required for a rainbow is incredibly specific.
How so?
The sun must be shining behind you. As the sunlight enters a tiny water droplet in front of you, it refracts and disperses, unzipping into its colors.
Just like the glass.
Exactly. Those colors hit the inside back wall of the water droplet and reflect perfectly back toward you, refracting one more time as they exit the water. You are witnessing millions of tiny droplets performing this exact optical sequence simultaneously.
It's a massive coordinated optical illusion powered purely by water and geometry.
It really is.
But if a tiny microscopic water droplet can act as a prism to bounce light around, we have to consider what happens when the entire Earth's atmosphere acts as a giant swirling optical lens.
Now, this is where the physics get truly mind-bending. The Earth's atmosphere is not a static, uniform dome of clear air.
Right, it's messy.
Very. It is a chaotic, turbulent mixture of hot and cold layers. And the crucial physical rule here is that hotter air is less dense than cooler air.
Okay, that makes sense.
Because of that density difference, hot air and cold air have slightly different refractive indexes. They bend light differently. You can see a localized version of this if you look over the top of a hot bonfire or a scorching asphalt road. The air wavers and completely distorts the objects behind it.
So scale that local bonfire up to the entire atmosphere covering the planet, and you suddenly have the explanation for why stars twinkle. Exactly. Because starlight travels perfectly straight through the empty vacuum of space for millions of years. But the very second that light hits our atmosphere, it has to pass through these constantly shifting, boiling layers of hot and cold air.
And because the stars are so incredibly distant from Earth, they act as tiny, singular point sources of light.
Just a single speck.
Right as that single fragile point of light gets knocked around and bent by the fluctuating atmospheric density, its apparent position shifts slightly from our perspective on the ground, and the amount of light successfully hitting our eye flickers.
And that constant atmospheric flickering is what we perceive as a twinkle.
Exactly.
But if you look up at the night sky, you might notice that the planets like Venus or Jupiter, they don't twinkle at all. They just shine with a steady glow.
They do.
And the reason why is so elegant. Planets are much closer to Earth, so instead of being a tiny point of light, they act as an extended source. You can think of a planet as a collection of many point sources of light packed closely together to form a tiny disk.
Yes, that's exactly right.
Because there are so many overlapping points of light coming from the planet, the atmospheric bending of one point is basically canceled out by the bending of another point right next to it. The wobbles average out to zero, giving you a steady shine.
It's a beautiful piece of optical logic. But atmospheric refraction does more than just give stars their romantic twinkle. It actually messes with our perception of time and physical space.
Oh, particularly during sunrise and sunset, right?
Yeah.
The advanced sunrise and the delayed sunset. Because the Earth is a globe wrapped in an atmosphere, that atmosphere acts like a massive magnifying glass that bends light downward toward the normal. It literally bends the sunlight over the physical curve of the Earth. Which means in the morning, the atmosphere bends the sun's image up to your eyes roughly 2 minutes before the physical mass of the sun has actually crossed the horizon.
Yep.
And in the evening, you continue to see the sun for about 2 minutes after it has physically dropped below the horizon.
It fundamentally alters your reality.
So to be totally clear about what this means, when I'm sitting on the beach watching a beautiful romantic sunset slowly dip below the water, you're telling me the sun is already gone and I am just staring at an atmospheric mirage.
I am confirming exactly that. You are looking at a delayed broadcast of the universe.
That is wild.
The actual physical ball of plasma has already set. The glowing orb you're watching is an optical projection bent over the horizon by the atmosphere. It is the ultimate proof that our eyes, no matter how perfectly that biological autofocus is working, do not always show us where objects truly exist in physical space.
That is going to completely change how I experience every sunset from now on.
It ruins it a little, doesn't it?
Just a little. But the atmosphere doesn't just bend light like a lens, it also acts like a massive color filter. Which brings us to the final piece of the puzzle. Why the sky is blue.
To understand the blue sky, we have to look at the scattering of light. Specifically starting with the Tyndall effect.
Okay.
The atmosphere isn't just empty space. It is a messy, chaotic soup of dust particles, smoke, water droplets, and gas molecules. When light hits these suspended particles, it scatters in different directions.
Right. You see the Tyndall effect when sunlight filters through the canopy of a dense forest or through a smoke-filled room. The beam of light becomes visible because the floating particles are actively scattering the light into your eyes.
Exactly. But the color of that scattered light depends entirely on the size of the particles doing the scattering. And this is the secret to the blue sky.
Okay, lay it on me.
The nitrogen and oxygen molecules making up our atmosphere are incredibly tiny. They're actually smaller than the wavelength of visible light.
Oh.
Yeah, because they're so small, they're highly effective at catching and scattering the shorter wavelengths of light, which sit at the blue end of the spectrum.
Meanwhile, the longer wavelengths, like red, just push through those tiny molecules much more easily, right?
Exactly. Red light has a wavelength about 1.8 times longer than blue light. So as pure white sunlight enters the atmosphere, the short blue waves get violently scattered in every possible direction by the air molecules, while the red waves push straight through.
Ah, I see.
So when you stand outside and look up at any part of the sky away from the sun, the light hitting your eye is that scattered blue light.
Which means if we didn't have this specific atmospheric soup to scatter the light, the sky would simply be dark, even in the middle of the day.
Yes.
It's like if you're standing on the moon where there is no atmosphere, you look up and the sky is pitch black.
Totally black.
But we actually use this exact same physics rule here on the ground for safety. Think about your drive to work. Why is every stoplight, every taillight, and every danger signal in the world painted red?
It is certainly not an arbitrary design choice. It is entirely driven by the physics of scattering.
Exactly. Because red light has the longest visible wavelength, it behaves like a massive off-road vehicle driving straight through a muddy swamp of fog, rain, or smoke. It just powers through.
Great analogy.
Thanks. Meanwhile, the short blue wavelength acts like a low-to-the-ground sports car that gets completely bogged down and scattered by the fog. Because the red light pushes through the atmosphere with the least amount of scattering, it can be seen clearly from much further away in dangerous weather conditions.
The symmetry there is just fantastic. The exact same physical phenomenon that paints our daytime sky a calming blue is precisely what we rely on to engineer life-saving red warning signals on our highways.
It's the invisible physics of light, practically applied to human survival.
It really is.
It's basically a masterclass in how everything connects. I mean, we started this deep dive looking at a tiny 2.3 centimeter sphere of jelly and muscle inside our skull.
We did.
We explored how it stretches and squishes to act as an autofocus lens, relying on our brain to instantly flip an upside-down electrical signal into reality. We talked about how we can share the profound gift of that vision through corneal donation, passing sight on to kids who desperately need it.
Such a crucial point.
And then we zoomed all the way out, unpacking how microscopic water droplets unzip white light into rainbows, how hot air projects time-traveling mirages of the setting sun, and how the tiny gas molecules in our air violently scatter blue light to paint the entire dome of our sky.
It is a phenomenal journey from biology right up to astrophysics.
Yeah.
And I want to leave you with a final thought to ponder, building directly on the mechanics we've explored today.
Let's hear it.
We've established that our human eye relies entirely on the specific, chaotic makeup of Earth's atmosphere to show us a blue sky, twinkling stars, and delayed sunsets. Our entire visual perception is filtered through this exact, local mixture of nitrogen, oxygen, dust, and water. But imagine for a moment what a colorful world would look like to you if you were standing on a planet with completely different atmospheric mixture.
Oh, wow.
Different gases, different densities, different particulate sizes. Your biological camera, your eyes would be exactly the same, functioning perfectly.
But the reality you perceive.
The colors of the sky, the behavior of the shadows and the light, it would be entirely alien. It makes you wonder, what other illusions of light are we simply accepting as absolute, unquestionable reality every single day?
Well, that is a thought that is going to keep me up tonight. Our eyes are brilliant, but they are absolutely showing us a filtered version of the universe. Thank you so much for joining us on this deep dive. The next time you go outside, take a long look up at the blue sky, watch the delayed optical broadcast of the sunset, and just take a moment to appreciate the incredible invisible physics happening right in front of your eyes.